All right, so our next chapter, chapter 4, revolves around this concept called aromaticity. That looks very incorrect spelling-wise. Well, I guess we're good. Okay. Not a strong speller. Okay. Anyways, aromaticity is this important concept. I think just to kind of rewind back to Chem 3A, there would have been a time where you were doing Lewis structures. So for example, the nitrite ion, NO2 minus 1, you would be drawing your Lewis structure for it. Okay? But if you do the correct Lewis structure for the nitrite ion, it's not just one structure, but you'd actually have to draw two of them, where you move this double bond into both positions, right? So my second structure here. All right, and so the difference, so drawing the Lewis structure for this, you would have learned that you have to actually draw two structures where the double bond is in these two different positions. Okay? And the whole shtick about why you couldn't just include one of these structures but had to include both is it turns out that this pair of electrons in this bond right here is not actually localized in one spot, but it's spread out between both positions at the same time. Okay? Electrons are quite magical little particles in that they don't have to just be at one place at a time. I imagine electrons more as like clouds that can kind of spread themselves out. And so when you draw both of these structures, the reason why you're including both of them is because this pair of electrons has spread itself out into both positions. Okay? These are what are called resonance structures. This idea of aromaticity is kind of going to build on that one step further. All right, the classic aromatic compound is what's called benzene. All right, this compound is somewhat synonymous with organic chemistry. It's a cyclohexane ring, but then every other bond is a double bond. Okay? And much like our nitrite ion, if we were being good, we would include both of these resonance structures for benzene, right, where I move these double bonds to the other position. All right, so just notice real quick, let's play the spy the difference game. What's the difference between these two compounds? I've taken each double bond and I've moved it over one step. All right, so benzene, how many carbons does benzene have? 6. So C6. How many hydrogens does benzene have? So let's look real quick at each one of these carbons here. If I look at this carbon, how many bonds does it currently have? 3, right? So 1, 2, 3. So then there's one hydrogen sticking off of this. Same for all of these. All right, because of that double bond, we got 6 carbons and 6 hydrogens. So C6H6, that's benzene. And these electrons in the double bond, they spread themselves out, right? These two resonance structures, neither one of them is true at any given time. The electrons in these double bonds, they spread themselves throughout the ring. All right, benzene was kind of an important concept compound in early chemistry because it really is what sort of introduced chemists to this idea of resonance structures and this idea that electrons can be spread out in more than one place at once, right? So again, if we take our benzene ring, just kind of redraw it. Every other bond is a double bond. All right, but again, in my mind, when I'm looking at something like this, I'm imagining that these electrons are actually spread out all throughout that ring. They're delocalized throughout that ring, okay? This was a weird concept for chemists because back in the day, it was really easy to kind of figure out what the formula of a compound was, but they didn't understand why this ring was so symmetric, right? Because if I had a ring where every other bond was a double bond, double bonds are shorter than single bonds, so I would expect it to look something, oh my gosh, this is going to be such a nightmare to draw. Something like this, with short double bonds and long single bonds, this very asymmetric sort of structure. And what all of their experiments were telling them was, no, you have this perfectly symmetric ring. All right, and so this kind of birthed this concept of this idea that electrons can move about. They can be in more than one place at a time. Okay? Along the same time, they were coming up with what's called molecular orbital theory or atomic orbital theory. If you remember back to general chemistry, that 1s2, 2s2, 2p2, all that jazz, right? These electrons, they live in these orbitals that have these different shapes associated with them. All right? One thing that we didn't really talk about with alkenes too much is the shape of that double bond, right? So it turns out that a double bond, one of those bonds, so hold up, if I have a simple compound like ethene, all of these bonds here, all my single bonds, and one of those bonds in my double bond are what are called sigma bonds. All right? Sigma bonds are kind of like exactly what you would expect a bond to be, right? A covalent bond is the sharing of electrons. It just means that if me and you are sharing electrons, those electrons are sitting right in front of us, right? We're sharing these electrons that are directly between these two atoms, right? So this carbon right here, let me get a better color. This carbon right here, and this carbon right here, right? They're bound together by a single bond, a sigma bond. Those electrons are just being shared directly between those two atoms, right? Kind of, again, exactly what you would think a bond would be. Just electrons being shared directly between two atoms. Nothing crazy, okay? The other bond, though, the second bond, is what's called a pi bond. Okay? Those carbons, they have these p orbitals. Remember, those p orbitals are these peanut-shaped things. They're actually sticking out above and below this carbon atom. All right? And so it's two carbons, their neighboring p orbitals are what's forming this second bond, this pi bond. All right? So again, if me and you are double bonded, one of those bonds is a sigma bond where we got that electron density directly between the two of us. But the other one, my electrons are pointed up and down, and we're overlapping that way. Okay? So the shape of those pi bonds is to stick out both above and below that plane, that flat double bond. Right? So if I were to sort of try to, oh my gosh, it's going to be a nightmare to draw. Here's my carbons. They got one direct sigma bond. Okay, so now I'm going to draw it as if I had taken this structure and rotated it. All right, so my hydrogens are pointing out and into the page. That second bond is going to be above and below. And it's the overlap between those orbitals that are sticking out above and below that forms my pi bond. All right, so then how the heck does this tie into what we were just talking about delocalized electrons? Because if I take a ring that has a bunch of double bonds in it, like benzene, now all of those p orbitals are sticking up either above or below that ring. All right, they're all pointed in the same direction. So this is just my benzene ring. But now I've flipped it on its side. That ring is a flat shape. And I got these p orbitals sticking out both above and below that ring. Okay? The electrons that live in those p orbitals, because they're all nicely aligned, everything's just like stacked up right in a row, they can just kind of zip themselves around through those orbitals. Okay? So again, the nature of a double bond is these little shapes right here, these peanut shapes that stick out above and below. All right? So if I have a ring of them, then I got a ring of those peanut-shaped orbitals. Every carbon's got one sticking up and one sticking down. The electrons that live in those orbitals can then kind of just zip around that ring really easily because all those orbitals are lined up one next to one another. Okay? So this is an aromatic compound. It's a ring of delocalized electrons. Okay, so again, benzene is a ring of delocalized electrons. What do I mean by delocalized? Electrons can spread themselves out across multiple carbons. Oops. All right, so this chapter, aromaticity, is going to deal with these aromatic compounds. Again, they're all going to have these rings of double bonds, and the real special thing about them is within that ring, the electrons are able to spread themselves out. All right, and so these are going to give these compounds some unique properties. Benzene, by far the most famous aromatic compound that exists, but it's not the only aromatic compound. All right, so the first skill that we're going to need to learn here is how to spy an aromatic compound. All right, much like what we've done before, we're going to have this set of rules, and we're going to need to apply that set of rules to different compounds. All right. So, our rules for aromaticity. Okay, rule 1, the compound must have a fully conjugated ring. Okay, and so what do I mean by conjugated? All carbons must be in one double bond. Okay, so again, we're going to use benzene as our sort of like example here, and again, we'll apply these rules to a bunch of different compounds, but benzene's the one that we know is aromatic, right? So let's just make sure that we can convince ourselves that benzene does follow this rule. Okay. So how am I going to tell if a ring is fully conjugated? I'm going to look at each carbon, and I'm going to make sure it's participating in one double bond. All right, so I'm going to go to this carbon here. All right, great. It's got a double bond associated with it. This carbon here, okay, great, has a double bond associated with it. All right, this carbon here, all of these carbons are participating in one double bond. That makes this a fully conjugated ring. All right, so check, check. We got a conjugated ring. All right, so let's take a look at something that would not be a fully conjugated ring. Right, I'll do again another 6-carbon ring, but now I'm only going to put 2 double bonds in there. So again, I'm going to go around my ring and look at each carbon. Okay, this one's got a double bond associated with it. This one's got a double bond associated with it. This one's got a double bond associated with it. This one does too, but now all of a sudden I get to these ones, no double bond in sight. No double bond in sight. All right, so I don't have a fully conjugated ring. I got these 2 carbons in there messing everything up. Okay, so this is not conjugated. Not a conjugated ring. Let's look at another one. If I look at this, all of these carbons have double bonds associated with it. Why does this still not satisfy rule 1? Because it's not a ring. All right, so those are our 2 criteria that we're going to look for. We need a fully conjugated ring. So all of those carbons need to be participating in a double bond, and it has to be a ring. All right, so this is not a ring. Okay? Our second rule is that there must be an odd number of our conjugated electron pairs. All right, so we're going to kind of build off this, but when in terms of counting conjugated electron pairs, the first thing we're going to look for is counting those double bonds. All right, so again, let me try to make a little bit more room for myself. Again, we got benzene. We established that it was that fully conjugated ring, right? Satisfied rule 1. So now let's convince ourselves that it also satisfies rule 2. If I'm going to count my conjugated pairs of electrons, remember each one of these double bonds, this represents a pair of electrons being shared. So I got 1, 2, 3. I indeed have that odd number. 1, 2, 3 pairs of electrons that are conjugated in this ring. Another term that we're going to hear for this same sort of concept that I've used before, so let's just say it again. This is delocalized electrons. Right? And again, if you just think about that word, localized would mean put in place in one location. Delocalized means that it can spread itself out. All right, so these 3 pairs of electrons in this benzene ring are spread out throughout that ring, right? That's what makes this compound aromatic. All right, but let's look at another compound here. Does it satisfy rule 1? Is this a fully conjugated ring?
Yes.
All All right, so if I go to each carbon, literally the way that I do it is I look at each carbon and I just color it. Okay, this one has a double bond associated with it. This one has a double bond. This one has a double bond. This one has a double bond. If I can color all carbons in a ring, then it's a conjugated ring. All right, so check, check. This satisfies rule 1. But now let's look, what about rule 2?
No.
How many pairs of electrons do I have? I got this one here and this one here, so I got 1, 2. I have an even number of electron pairs. So this violates rule 2. Okay, so this compound, even though it's a fully conjugated ring, it would not be considered an aromatic compound. Compounds that satisfy rule 1 but violate rule 2 are what are called anti-aromatic. And then let's take a look. We also had this previous example here. We said, all right, well, these carbons are conjugated. However, these ones are not. We do not have a fully conjugated ring. So we said that this compound here violated rule 1. If it violates rule 1, we're not even going to go on to rule 2. We call these compounds non-aromatic. All right, so first thing that we're going to need to do is, given the structure of a molecule, we should be able to put it into one of 3 bins. Remember benzene. We said it satisfied rule 1 and rule 2. Right? Check, 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 check. That's what made this compound aromatic. If you satisfy rule 1 but violate rule 2, you're anti-aromatic. And if you don't satisfy rule 1 from the jump, then you're just non-aromatic. All right, but given a structure, we should be able to classify it in one of these 3 categories by applying those 2 rules. All right, so let's just do a bunch of examples here. All right, so take a second and see if you can't classify these compounds as being aromatic, non-aromatic, or anti-aromatic. All right, so for this very first one here, let's take a poll here. Who thinks that this is aromatic? What about anti-aromatic? And what about non-aromatic? Awesome. So, all right, I'm going to do my ring. This carbon has a double bond. So does this one. So does this one. So does this one. But all of a sudden, I get to this one, and it's messing it up. It does not have a double bond associated with it, so that violates rule 1. Making this non-aromatic. All right, what about my stop sign? Who thinks it's aromatic? What about anti-aromatic and non-aromatic? Yes, this is indeed anti-aromatic. If we go around our ring, everything has a double bond associated with it. But then I move on to step 2, where I start counting these pairs of electrons. And I get 1, 2, 3, 4 pairs of electrons. All right, so I don't have, whoops, that's not how counting works. I don't have my odd number, I have an even number of electron pairs, so that makes this anti-aromatic. All right, what about this one? This one's a little tricky. I got what's called a fused ring going on here, right? It's like 2 6-membered rings stuck together. If I'm going to figure out whether or not this ring is fully conjugated, I'm just going to do the same thing, right? This carbon has a double bond. This one does too. These ones are all good, right? So everybody hopefully can convince themselves that all those carbons have a double bond associated with them. I'm just going to move on to the other ones. These ones do as well, right? So do I have my fully conjugated ring? Yes. So now I can move on to counting electron pairs. 1, 2, 3, 4, 5. I got my odd number, so this compound is indeed aromatic. These electrons can not only spread themselves out within that one ring, they can actually spread between both of those rings, right? We got this massive network of delocalized electrons. Okay? So, classifying compounds as aromatic, non-aromatic, or anti-aromatic. The other thing we want to be able to do is answer how many delocalized pi electrons are there. All right, how many electrons are there that can spread themselves out? Okay. And the sort of important thing to realize here is that even though this ring is not fully conjugated, these 2 bonds, since they're 2 pi bonds next to each other, they can still spread themselves out. They can only go back and forth and back and forth and back and forth. They can't do the full ring, right? So we can't classify them as aromatic. But because there are 2 pi bonds next to each other, we still have 4 delocalized pi electrons in this compound. All right, so when we're asking ourselves how many delocalized pi electrons, we're going to count any pi bonds that are next to one another. And we want to remember that each pi bond contains 2 electrons. All right, so for our other examples, take a second and see if you can't tell me how many delocalized pi electrons there are in each of those other 2 compounds. right, so here we said there were 4 pi bonds. They're all spaced next to one another. So then how many delocalized pi electrons do I have? 8, right? Each bond contains 2 delocalized. So there's 8 delocalized pi electrons there. And here I have these 5 pi bonds, so that would be 10 delocalized pi electrons. All right, so those 10 electrons are allowed to spread themselves out to any position on that ring. All right. So now, what about carbocations? Let's say that I have a ring. Okay. We said that this here, we did this previously. And we said that this was non-aromatic because of this guy right here messing everything up, right? Breaking the conjugation of that ring. But what if we had the same compound, but now that top carbon, instead of being neutral, is a carbocation? All right, so the important thing about carbocations to understand is carbon, when it has this positive charge, it has 3 bonds associated with it, but no lone pairs. It actually has an incomplete octet, right? Turns out that that missing pair of electrons is missing from an empty p orbital. Okay? And remember, the whole shtick about this conjugation, the whole reason that we're looking for those pi bonds is because those are those p orbitals that are sticking up, right? So a carbocation, although it doesn't have any pi bond associated with it, it still has a nice empty p orbital, okay? So what does that mean? That means carbocations, they do not break the conjugation of a ring. So when I'm going around and I'm looking to see if I have a fully conjugated ring, I'm going to color these 4 carbons here because they have these double bonds associated with them. But I'm also going to color that carbocation because it also has that empty p orbital. It can accept electrons in there, right? So the bottom line is we're going to also count our carbocations when it comes to the conjugation here. All right, so this compound with that carbocation does not violate Rule 1. I get to color all of those carbons in a line. So then I'm going to move on and see if it applies, how Rule 2 applies. Right? We've ruled out this compound is not non-aromatic, but is it aromatic or anti-aromatic? Anti. So how many pairs of electrons we got? 1, 2. Right? So we have an even number of electron pairs, so this would be anti-aromatic. So carbocations, Two things that we want to note. They do not break the conjugation of a ring. Notice they also don't have any electrons associated with them, right? I didn't count that carbocation when I was counting electron pairs. There's no electrons associated as well. All right, so let's just do a few more examples here. All right, so let's go through these in our last few minutes here. Again, I need to see if rule 1 applies. I'm going to go and I'm going to count every carbon that has a double bond associated with it. This one counts. This one counts. All right, but then we also are going to count our carbocations. Remember, they don't mess up the conjugation of the ring, so this one also gets a little marking here. Okay, so that means that we indeed have a fully conjugated ring. So now I get to move on to the next step, counting these electron pairs. I have 1, 2, 3, 4, so that makes this compound what? Antiaromatic. Go to this one over here. This is a little weird, and granted my drawing's not great, but we got 2 5-membered rings, 2 pentagons fused together. All right, so again, I'm just going to count each carbon that has a double bond associated with it. Should I count this one? Yeah, what about this one? All right, these ones that are at the intersection can be kind of hard to see, but you just need to look at that carbon and say, is there a double bond anywhere? All right, so each of these, I got my conjugated ring. I'm going to move on to counting electron pairs. 1, 2, 3, 4. So this is also anti-aromatic. What about this one here? Anybody? This would be non-aromatic, right? Because although these are all conjugated, they all got that spacing, I got this one right over here messing it up. So I don't have a fully conjugated ring. This one is non-aromatic. And then all of a sudden, if I make that top carbon a carbocation, now all of a sudden when I'm counting my carbons, I am going to include that carbocation. So this one satisfies rule 1. We got a fully conjugated ring, and we have 1, 2, 3 electron pairs. So that makes this aromatic. Cool. All right, so that's what we need to be able to do for our homework this weekend, is again to classify compounds as one of those 3 categories: non-aromatic, aromatic, or anti-aromatic. Again, because those are your only 3 choices, maybe you can guess your way through it and don't really know why you got it right or wrong, but of course that's not the name of the game, right? So make sure that you understand how to apply these rules. What's up?